Morning, everyone. Hope you all had a good weekend. Ready to get started here. Were there any questions over anything?
I was having trouble with some of the homework.
Okay.
Some of the questions that they would give us, I don't remember us going over in class.
Okay. Was there a particular problem?
There were a couple different ones. I did the question help and was able to figure it out. But let me see if I can get to it real quick.
Let me see. Did I post the video for 8.4?
Yeah, we did 8.3 and you posted the video for it. Yes, sir.
For 8.3, right?
Yes, sir.
Okay.
Yeah, for 8.3, there's no 8.4.
Yeah, there's no 8.4. That's what we're doing today. So, okay, I just want to make sure I did do the video. Maddie, was it over 8.3 that you had issues with?
Yes.
Okay.
Yeah, 8.3 got a little weird, but you talked about it in the video.
Yeah, I really don't like the way that the homework system, whoa, where'd that go? I really don't like the way that this homework system does these problems. Let me see. All right, so do you remember which one, Maddie, or do you want me to just kind
I think it was like question 11 and 12 or like the type of questions, I think. Not positive though.
Let me see. This one seemed, I think that, I don't know, is that it? Because I think we did kind of cover something like that.
No, that wasn't it. But I can go back and rewatch the homework video.
Okay, yeah, let me know if you have some trouble. There were the problems with the calculator. Those were the ones that were weird.
Yeah.
Yeah. Okay, let's start with today's stuff, and then if we have some time at the end, maybe I'll answer some questions. Is that all right, Maddie? All right, let me close this out. All right, so today we're still a little bit behind. We're a day behind. We're supposed to start trigonometric identities today. So let's get started with that. Now, this section, when I look back on it, I remember when I took pre-cal, and this section, I remember it being very hard, but I don't want to make it out to be worse than it actually is. It's very different than anything that you probably have ever done before. So that's why it's going to look strange at first, I think. So let's just see how this goes. There's a couple of definitions, and then once we get to the definitions, once we get these out of the way, then it's right into the problem. So trigonometric identities. First, you have to know the difference between saying something. If you have an equation, okay, so if someone gives you an equation, to say whether or not it's an identity versus what's called a conditional equation. All right, so I'm going to give you an example over here on the side. So if I write this down, sine squared theta plus cosine squared theta equals 1. That's something that we've already talked about in this class, haven't we? We've talked about this is the Pythagorean identity, and it's something that is always true. Okay, so this is always true. In other words, if you replace theta with any number you want, this equation will always equal to 1. And so we call this an identity. Okay, it's the Pythagorean identity. That is different than something like this. Oh, I should point out, see that it's an equation, right? It's got an equal sign, so it is an equation. But because it's always true, no matter what x you ever plug in, we call it an identity. Compare that to this. 2x plus 1 equals, let's say, 5. Okay, that is also an equation, right? but it is not an identity, because you cannot plug in any value you want for X and have this be true. There's really only one value of X that you can plug in, and that's, it's true if, right, if X equals 2. If X equals 2, then 2 times 2 plus 1 is 5. So this is a conditional equation. The condition is that X has to be 2 for this to be true, as opposed to the other one, which is an identity, because it's always true regardless of what you plug in. Do you understand the difference? Conditional versus identity. Okay. Now, with that said, these are the identities that we have coming in right now. We should all be comfortable with these identities. So these are true, these equations, right? These are all equations. These equations are true no matter what theta you plug in. Okay, these will always be true. So the first are the quotient identities. We know that tangent theta is sine over cosine. We know that cotangent theta is cosine over sine. The reciprocal identities, we should know these. These are all in our formula sheets. The Pythagorean identities, and remember when we did Pythagorean, I said this is the one you need to memorize. The other two you should be aware of. All right. If you can memorize them, great. If not, just know that they're here. Okay, we will be needing these today. And then you have the even and odd identities, and we did talk about this also. Do you remember me talking about the sign? When you plug in a negative angle, it's the same as plugging in the positive angle, but changing the sign. We call that an odd function. Then this was even, this was odd, and then the reciprocals are the same things. So these are the things that are identities. They're always true regardless of what theta we plug in, and that's it. All right, those are the identities we have. Okay, now what is today about? Today is about.
Can you go back to the very first identity? I missed a couple of things about it.
Right.
About that.
Oh, up here.
Yeah. Thanks.
Okay. Let me know when you're done. And remember, all of this is also in the ebook. I had trouble opening the ebook last night. I tried to open it and it wouldn't open. Did anyone else have any trouble with the website last night?
Yes, sir. I did until about like 11:40 last night.
Oh, really?
It was just like a blank screen and wouldn't load.
Yeah. Yeah, that's what happened to me last night too. You good, Maddie? Yeah, okay. All right, so what is today about? Today is about what we call verifying an identity. Okay, so we're going to be presented with something, all right? And we're supposed to verify that it is an identity, all right? So the first example we have here is not verifying identities. It's just getting us to get a feel for the type of algebra that we're going to have to do. And today is going to be a lot of algebra. All right. So let's look at this first example. It says simplify cotangent theta over cosecant theta by rewriting each trigonometric function in terms of sine and cosine. All right. So for right now, don't worry about why we're doing this or what's the ultimate goal. Let's just do what they're saying. So we're going to take cotangent theta over cosecant theta. And what they want us to do is rewrite this by replacing things with sine and cosine. So cotangent theta, we know from the identities, and I'm not going to refer back to this every single time, but we know that cotangent theta in terms of cosine and sine is cosine theta over sine theta. So I'm going to write that down. The top is cosine theta over sine theta. And then that's all divided by, and then cosecant theta is 1 over sine. So 1 over sine theta. Now we have a fraction on top and a fraction on the bottom. And so anytime you take a fraction, divide by another fraction, it's the same as taking the top fraction and multiplying it by the reciprocal of the denominator. And the reciprocal of 1 over sine is sine theta over 1. And do you see that if we cancel out the signs, this is equal to cosine theta? Make sense? So looking at this expression, that's just a fancy way of writing cosine theta. You'll see that? So what the point of this first example, part A, is to show us that when we get things that involve like cotangent or tangent or cosecant or secant, that when we rewrite things in terms of sine and cosine, sometimes things get nicer, okay? So just be aware of that. We can always rewrite things in terms of sine and cosine. All right, let's look at part B. It says, show that this is equal to this by multiplying the numerator and denominator by 1 minus sine theta. I think I'm going to grab this and go do this on another page. All right, so they give us this expression, and what we want to do is multiply the numerator and denominator by 1 minus sine theta. Okay, so let me see if this makes sense to you. You might be asking yourself, why would I multiply by 1 minus sine theta, right? They're telling you to, right? They're telling us to multiply by this. They're not telling us why to do that, right? They're just telling us, hey, look, do it and see what happens, all right? See what happens. We're going to multiply the numerator and denominator by that. Okay, so what we'll do is, and this is a very, very important part of this whole technique today. We have an equation, right? What we're going to do is we're going to start with one side of the equation. We're going to start here. And what we're going to do, our goal here is to turn it into the right side. Okay, so I'm only working with one side of the equation. And I'm going to multiply the numerator and denominator by 1 minus sine theta. Again, don't worry about why it's 1 minus sine theta. It's just because they're telling us to, right? Okay, on the numerator, I have 2 terms in this parentheses, and I've got to hit the cosine with it. So the cosine is going to have to distribute through. On the bottom, I have 2 terms and 2 terms, so I will have to FOIL the bottom out. All right, so let me do the top multiplication first. So when I do cosine times 1, sorry, cosine theta times 1, I get cosine theta. And when I do cosine theta times negative sine theta, I get negative, well, just sine theta, cosine theta. I can't really do anything other than put those next to one another. And then over, okay, how about this FOILing out here? Get 1 here. I get plus sine theta. And then when I do the middle one, watch what happens. I get negative sine theta times 1, that's negative sine theta. And then what would the last one be when I do negative sine theta times positive sine theta?
Would it be negative sine theta squared?
It'd be negative sine theta squared. Now, the way I'm going to write that is with the 2 right there. Remember, this 2 really means, it really means the whole thing squared, right? Those mean the same exact thing. Okay, so does everyone agree this is what I have? Okay, now the middle terms cancel. That's the good thing, right? The middle terms cancel. And we're left with cosine theta minus sine theta times cosine theta over 1 minus sine squared theta. Okay, so we're supposed to show that this equation right here, this left side, okay, really is equal to the right side. That's what we're trying to show, that the left side is equal to the right side by multiplying the numerator and denominator by 1 minus sine theta. So we did the multiplication. Here's what we got, and here's where we are. Can you all see that this right here is not the right side? It's not, right? But there's still some more things we can do. Does anyone see any algebra that we can do here?
What about the two cosines on top?
Okay, so I have a cosine here and a cosine here. They appear in
We
both
could factor
terms.
them out, right?
We could factor a cosine out, okay? And that's actually a good thing, because if we factor a cosine out of the top, we're left with what? We factor a cosine out of this and a cosine out of that. So when we factor it out of this, what are we left with?
1 minus sine theta.
1 minus sine theta. And do y'all see right now that we were trying to make it look like 1 minus sine theta on the top? We have 1 minus sine theta right now. Now we don't have like this doesn't have a cosine, this one does, right? You'll see that? But we're at least getting a little closer.
The bottom's the Pythagorean identity, correct?
Yeah, so if we look at where we're trying to go with this, we know that the green we've got matching. The denominator needs to be cosine theta. We don't have cosine theta, do we? However, if we recall, like Anna Marie said, if we recall that the Pythagorean identity, okay, so I'm going to write this down. This is actually, I should write this on the side. We know that sine theta squared plus cosine squared theta equals 1. If we were to move the sine squared to the other side of that equation, it would turn into cosine squared theta equals 1 minus sine squared theta, wouldn't it? And that's exactly what we have down. 1 minus sine squared theta. So I can replace 1 minus sine squared theta with what?
Cosine.
With the
Cosine squared theta, right? So I'm going to replace that here with cosine squared theta. And now do you see what happens? I mean, this cosine squared theta really means, if we wanted to write it a different way, this really means cosine theta times cosine theta. So what can I do with this cosine here and this one here?
Cancel.
Cancel them out. I can cancel one of the cosines, right? One of them. And then my final result is, let's see, the cosine on top's gone, so 1 minus sine theta, and the bottom is just cosine theta. And that is what I was trying to show. All right, let's back up. In order for us to show that these two are equal to one another, right? In order for me to prove it to you that these are the same expressions, in order for me to prove that this is an identity, right? This is an identity. These are equal to one another always. To do that, we had to multiply the numerator and denominator by 1 minus sine theta. Which again, I said, when would you have ever, come up with 1 minus sine theta on your own? Well, now you know you can, but let's think about why it worked. When we did 1 minus sine theta, do you see on the bottom we have 1 plus sine theta? And so these are conjugates. And when you do conjugates together, what happens is your middle terms always cancel, right? Those middle terms will always cancel when you do conjugates. And so what we'd be left with, or what we were left with, was 1 minus sine squared theta, which we can use a Pythagorean identity on. So moving ahead, let's just always be aware that if we have something like 1 plus sine theta, or 1 plus cosine theta, or 1 minus cosine theta, or 1 minus sine theta, that we might want to come in with a conjugate. It might help us, okay? So it's just, we're going to add that to a technique. Maybe we'll use it, maybe we won't. Understand? Questions? So the first thing that we learned here in part A was that if we turn things into sine and cosine, sometimes things get easier. The second thing that we've learned here is that sometimes we can multiply the numerator and denominator by this conjugate thing and things will get better. So let's look at the next one. These are all just what we're doing on this example is we're just learning some of the techniques that we're going to use to do these problems today. We actually haven't even started doing problems yet. Okay, so we want to write this, rewrite this, simplify this. Okay, the instructions are to simplify this by rewriting an expression as a single ratio. So we have 1 plus sine u. Okay, they're using u instead of theta over sine u plus cotangent u minus cosine u over cosine u. All right, so when it says to rewrite it as a single ratio, they mean get it to be a single, like a single fraction. So what are you thinking? Anyone have a thought on how we could write this as a single fraction? What do you need to do?
We got to get it all in either terms of cosine or sine.
Okay, so
We find a common denominator, right?
yeah, if we have two fractions that we want to add together to make a single fraction, we usually need a common denominator, right? I mean, that would usually help us out quite a bit to have a common denominator. So why don't we try that now, Joshua, to get things in terms, all in terms of sine or cosine. That might be our technique later as we move further into this. But let's just try and do like the basic algebra stuff that we know of. When you want to add fractions, we need a common denominator. So I need to multiply this fraction over here by cosine u on the top and bottom. And then this fraction over here I have to multiply by sine u. Y'all agree with that? That would give us a common denominator of cosine u times sine u. And on the first fraction, since I have two terms, the cosine must distribute. And on the second fraction, since the numerator over there has two terms, the sine must distribute. All right, so let's do the first fraction. The cosine u times 1, that gives me cosine u. Plus, let's see, cosine u times sine u is, well, doesn't matter what order I write this. I'm going to write sine u, cosine u. Is everyone okay with the idea that I could have put the cosine in front of the sine or the sine in front of the cosine because it's multiplication, doesn't matter? Okay, all of that is over the common denominator now, which I'll put sine u, cosine u. And then plus over here, when I distribute through, I'm going to put sine u cotangent u minus sine u cosine u all over the common denominator, which is sine u cosine u. Any questions there? Just getting your common denominator. Now it's time to put them together, right? So this is equal to, let's see, just all these numerators together. So cosine u plus sine u cosine u plus sine u cotangent u minus sine u cosine u, the whole thing over sine u cosine u. Now, I agree at this point we have a single fraction. Do you all agree we have a single fraction? And that's what the instructions said, but there's still some stuff we can do. These two cancel, don't they? Those two cancel. And now we have cosine u plus sine u cotangent u over sine u cosine u. I would argue at this point that we do have a single ratio. Do y'all agree? Is there anything else that maybe we could do that would simplify this a little bit more?
Maybe can we look at one of those equations?
How do you mean?
Just how like on the last problem we used the sine squared theta plus cosine squared theta, and that kind of
Okay, like a Pythagorean identity.
Could we factor sine u cotangent u?
So
You
first,
could take cotangent u.
hold on, with what James said, if we're gonna use Pythagorean, we need to have squareds in here. And nowhere do we have anything squared, right? So we can't use Pythagorean. Remember, Pythagorean says sine squared theta plus cosine squared theta equals 1. It does not say that the same holds if you don't square them, right? That's not true. So we have to have squareds in order to use Pythagorean. Now, Joshua said, I don't know what Joshua said, actually, I forgot. I know Joshua was saying something, but I forgot.
I was thinking maybe we could try factor sine u cotangent.
Oh yeah, factor sine. So this, the bottom has a sine, this has a sine, this one doesn't, right? It'd be nice if this had a sine, then we could factor out both of them, couldn't we? And we don't want to split it up into two fractions because that's where we just came from, right? We just had this as two fractions. We don't want to split it now. And then I heard what Maddie, you said one more thing. I heard
You can take cotangent and convert it to cosine theta over sine theta. So cosine u over sine u.
Yeah, what would happen there? What if we left everything alone? Right, leave everything alone. And converted, Maddie, what would cotangent u turn into?
Cosine u over sine u.
Cosine u over sine u. Right, that's the definition of what cotangent is. And Maddie, does that allow us to cancel these signs?
Yes, sir.
It does. So everyone needs to be aware that this sine u is really like a sine u over 1. And that's why these cancel. And so all you're left with now is cosine u plus another cosine u over sine u cosine u. Okay, in the numerator, any questions there? Cosine u plus cosine u. All right, no? Now in the numerator, cosine u plus cosine u, what would that give you?
2 cosine u.
2 cosine u. So be careful, not cosine squared, because you're not multiplying them, right? You're adding them. If you have an apple plus an apple, you get 2 apples. So here's where we are. Okay. And now what?
Then we could cancel a cosine.
You can cancel a cosine. My goodness, is this ever going to end? Okay, and now we have 2 over sine of u. But that's the same as 2 times 1 over sine of u. Right? Do y'all agree a 2 on the top is the same as a 2 out front and then 1 over sine, right? And what's 1 over sine?
Cosecant.
Cosecant. Oh my goodness, come on. Wow, okay. Whoa. So what that all meant, okay, what this all means is that, I need to go a little smaller, is that this expression up here, this nasty, ugly looking thing right here, is just a very complicated way of writing 2 cosecant u. This is an identity. If you wanted to, you could write 2 cosecant u equals that. Any questions? So common denominator, things canceled, put things together, rewrote cotangent as cosine over sine, sines canceled, put the cosines together, cosine canceled, 1 over sine is cosecant. Okay. So this is, you're starting to get a flavor, you know, for what we're going to be doing here. It's going to be a lot of algebra and cleaning things up, making things look a certain way. Okay, let's look at the last one.
I had a quick question.
Yeah, go ahead.
About the common denominator.
Yes.
I know how you said that like when we multiply, it doesn't really matter where you put like the sine or the cosine.
Mm-hmm.
But if you had a minus cosine, would it matter then which order you put it in?
A minus cosine where?
When you're multiplying. So like if you have a cosine u times sine u in the like the 1 plus sine u, if you were to multiply those and it was a minus, would it matter where the cosine u or sine u, like which order they went in?
Okay, so like if you're going to multiply cosine u times negative sine u, is that what you're saying? Like, let's say we're going to do that multiplication.
Yeah. Would it
Okay.
matter like where the minus was?
It
Would it
would
have to
not
stay
matter.
with the sign?
Nope, you could stay with sine. Normally what we would do is we bring the negative out front. And then you could say like sine u cosine u, or you could say negative cosine u sine u. Think about it this way. Okay, I think this will be easier for you to understand. If I said what's 3 times negative 4, okay, what are you going to do with the negative? Put it out front, right? And you're just gonna go 3 times 4 and give me negative 12, right? That negative out front, you could say negative 3 times 4, or you could say that that's negative 4 times 3. It doesn't matter where the minus sign is. It just has to be on one of them or out in front of everything. Does that make sense, Anna Marie?
Yes, sir. Thank you.
Okay, good question. All right, so where are we? I think we're going to try and do this one now. Simplify this expression, and you must admit that that's a pretty ugly looking expression, right? Simplify that by factoring. Okay, I don't know. Let's see what happens. Sine squared v minus 1 over tangent v sine v minus tangent v. Okay, they say factoring, right? But they're not telling us like any particular type of factoring. So does anybody see anything we can factor here?
You could factor out the tan from the denominator.
Okay, we can factor a tangent from the denominator. I agree. So in terms of factoring, what we're doing right now is we're doing a GCF, the greatest common factor. We're pulling a tangent v out of the bottom. We're left with sine v minus 1. Yes? Okay, now can we do anything now? Can you cancel here or no?
At the top, it's like a difference of squares where it's like sine v plus 1, sine v minus 1.
Good, good. So we cannot cancel. You cannot say that these signs cancel. And the reason why is because you have subtraction down here. If this was all multiplication and there was multiplication up top, you could cancel. But you are not allowed to cancel these just because they both have sign in them. But Jackson, I think that was Jackson that said that, is recognizing, and this is what everyone needs to recognize, is that that is like a difference of squares. That is like x squared minus 1, which we all know because we're in pre-cal and we passed college algebra, that factors to be x plus 1 times x minus 1, right? That's what x squared minus 1 would look like. But instead of x, we have a sine v, don't we? We have a sine v. So this is going to factor to be on top sine v plus 1 times sine v minus 1. And then all of that over tangent v. And then what was it? Sine v minus 1. Good. Now can you cancel anything?
You can get rid of one of the sine v minus 1s.
That's right. This can cancel now. And the reason it can cancel is because these are exactly the same now, and they're separated with multiplication here. So now you can do this. Okay, those are gone. And so what we're left with is sine v plus 1 over tangent v. And I would say at this point, we could probably say we're done. Okay. Because that, I think you would agree that this, this looks a lot better than that did, right? Like it's simplified. But I'm just going to show you that you could do something else. It's not going to simplify anymore, but I'm just going to show you could do this, and then we can debate whether or not this is better or not. How about this? What if I wrote that? And on the bottom, instead of writing tangent V, what if I wrote sine V over cosine V? Right? Now that doesn't, to me, look any better, but I just want to show you what you could do now is you can multiply the top and bottom by cosine V. On the bottom, it cancels, and on the top, just distribute it through. So you get cosine, cosine V sine V plus cosine V all over sine V. So I'm not saying that this is any more correct than this answer we got here. I'm just trying to get you to see that switching the tangent in terms of sine and cosine, we could get a different expression. The thing that's nice about this expression is that it has sines and cosines, and that's it. This one has sine and tangent, but it looks a little cleaner than this one. So you might be asking yourself, well, when do I know I'm done then, right? Like, when do I actually know I've achieved what I'm supposed to do? Well, like I said, we haven't done the problems yet. This was all just build up. Okay, now I think it's time for us to start doing the problems. All right, so we are going to now establish identities. Okay, now this is the main part now. This is what this section is about, establishing an identity. And I'm going to give you a set of steps on how to do this. Okay, it is almost always preferable to start with the side of the equation containing the most complicated expression. So anytime we're trying to establish an identity, we are going to start with either the left-hand side or the right-hand side of the equation. But you start with one, and then what you're going to do is you're going to start using different transformations with identities or whatever it is, okay? And you're going to try and turn that side into the other side. You might want to rewrite sums or differences of quotients into a single quotient. So you might want to put fractions together. Sometimes you might want to do everything in terms of sine and cosine, but always keep the goal in mind. And that is you are going to manipulate one side of the equation until it turns into the other side. Now this warning, I cannot express this to you enough here. When you're establishing an identity, you're going to be presented with an equation, and it is up to you to show that that equation is true. You are never allowed to work on both sides of the equation at the same time. And that's what you've been doing your whole life. When you're given an equation, you're told, oh, you can multiply both sides of the equation by something, or you can add or subtract a number on both sides of the equation. You're not allowed to do that because you are trying to show it's an equation that it's always true. So you have to start with one side and turn it into the other. So what you're going to see me do is this. You're going to see me write things like LHS. That stands for left-hand side. Or you'll see me write RHS, and that stands for right-hand side. And what we're going to be trying to do here is either start with the left-hand side and turn it into the right-hand side, or we're going to start with the right-hand side and we're going to turn it into the left-hand side. That's how this is going to work. All right. So it's going to be we're either going to be this or this. Okay, one or the other that we're going to do. All right, y'all ready to get started? Here we go. Now these start off pretty simple. All right. In fact, I'm going to just grab the first two here. We'll go work these. All right, let's establish this first identity. So we're looking at this identity. We are supposed to show that that's true. All right. So we have an equation. We have a left-hand side. And we have a right-hand side. Which side do you think looks more complicated? The left or the right?
Left.
Left. So let's start with the left-hand side. All right, left-hand side, you always want to start with the more complicated. Cosecant theta, tangent theta. Okay. What can I do?
You can change the cosecant theta into 1 over sine theta.
So cosecant theta by definition is 1 over sine theta. Okay, yes, I'm allowed to do that. Times
Sine of theta over cosine of theta.
sine theta over cosine theta. So that's just the definition of tangent, right? So rewrite cosecant in terms of sine and cosine, rewrite tangent in terms of sine and cosine. We get a nice cancellation here. We're left with 1 over cosine theta, which by definition is secant theta, which is the right-hand side. So do you see how I did this? I started with the left-hand side, rewrote it, canceled, rewrote, and that's the right-hand side. So you always have to start with one side and go to the other.
And this is showing that it's so if we went to find the right hand side, we would end up with the left hand side.
Well, you don't know. Imagine it that they're really asking you this, okay? Forget that secant theta is there, okay? They're really asking you to try and simplify this into something nicer, okay? And so what we say is, all right, it turns into secant theta. So that means that this is an identity, right? This is an identity. This is true, right? If I only have to go from one side to the other, left side to right side, I do not have to go from right side to left side because I've already established the identity by doing it this way. And it would be much harder to go from the right to the left because if you had started with the right-hand side, okay, let's say we'd started with this. Where do I go from there? Like, how do I make that turn into the left-hand side? Right, there's not much I can do here. I can say 1 over cosine theta, right? But now what? Do you see that I don't have like a clear direction to go here? I mean, I could go a lot of different ways. In order for me to make that the left-hand side, I would have to like miraculously say, okay, multiply that times sine theta over sine theta. I would have to like come up with that out of my own mind. And then I'd have to say, oh, slide that sine theta on top, sine theta over cosine theta. And then over here, I still have 1 over sine theta. And then I could say that's tangent theta and cosecant theta. But do you see that required this weird thought that just kind of, but I mean, I guess you could get it on a problem like this because it's not too bad. But do y'all see I had to like just fabricate that out of nowhere? That's why we always start with the more complicated side. The more complicated side gives us more to work with. And then what we're hoping is things cancel and go away and become the simpler side. Does that make sense, James? That the right-hand side, we don't want to go that direction?
Yes, sir. Yes, sir.
Okay. Let's look at the next one. So again, we have this thing, we're trying to establish this identity, right? And I would say that the left-hand side looks more complicated, would you? Yeah. So left-hand side is sine squared negative theta plus cosine squared negative theta. Okay, that's it. That's all I can write down. Don't write equals 1. This problem, what do you think of this problem?
Well, sine squared plus cosine squared, it's equals 1.
Yeah, as long as what's in here, right? As long as those are the same, then the answer is 1, right?
Mhm.
This is kind of a ridiculous problem. That's the
So
right
you
answer.
wouldn't need to rewrite like sine squared theta as negative sine squared theta?
You wouldn't need to, no, because they both have negative theta in them. They both have negative theta, right? Now, let me ask you this. That problem was too easy. I'm really not happy with that. It was too simple. Let me ask you a different problem. What would sine squared negative theta plus cosine squared of theta, would that be 1? Is that true?
No.
Okay, so let's see. Doesn't this really mean sine of negative theta squared plus cosine of theta squared, right? Let's start with the left-hand side. So is that true that when you say sine squared of negative theta, you really mean sine of negative theta, but then you're going to square it? Everyone agree with that? Now, this one has theta, this one has negative theta, but wait a minute, isn't sine an odd function? So that really means that that's negative sine of theta squared plus cosine of theta squared. So right there, from here to here, I'm using the fact that it's an odd function. If you need to go back and look, that's right here. That's the odd property of sine. Sine of negative theta is equal to negative sine of theta. Now, if I take this negative sine theta and square it, won't it be positive? So this really is just sine squared theta plus, let's rewrite that one back the way it normally goes. And the key again is because this -1 gets squared, right? This is like a -1 that eventually gets squared when I do the squaring here. Then this is now sine squared theta plus cosine squared theta, but that is 1, isn't it? And so even though it doesn't look like I should be able to use a Pythagorean identity here, I can because the odd property of sine. So this is the right-hand side. All right, let's do more. That one was too easy. You know what? Do just this one first. Okay, so what I think I'm going to do is allow you just a few minutes just to start thinking about how you would approach this. Okay, I just want to give you a few minutes. Maybe you can try a little bit of algebra. How about we take about 5 minutes just to see from what we've discussed so far today if you can do anything with this in 5 minutes. Remember, start with the more complicated side, work with it, see if you can turn it into the right-hand side. I do plan on calling on somebody here in a minute just to see if you got anywhere. Go one more minute. Okay, I think that's enough time. So I had the computer like randomly shuffle all your names again. And Brianna, you came up first. Are you there?
I'm here.
Okay, have any luck?
Sort of.
Okay, which side did you start with?
The left.
Okay, so what did you do? Or what were your thoughts here?
So I basically separated the squared, so I ended up with sine negative theta times sine negative theta minus cosine negative theta times cosine negative theta. Like I guess you
Okay,
could
yep.
back to it.
Let me catch up with that. I'll write that
Yeah, you
down. So Brianna decided to say, okay, the top is just sine negative theta times sine negative theta minus cosine negative theta times cosine negative theta, right?
Yes.
Okay, and then you just did that over the denominator. Did you do anything down here or just left it?
No, I just left it.
Okay, all right. Okay, now what?
And then I canceled.
How do you mean?
What? Like I canceled one of the sine negative thetas to the one of the sine thetas on the top.
Oh, like here and then like same thing over here?
Yes.
Okay, can you do that?
I'm guessing
Think about it this way. Whenever you do something algebraically that you're not quite sure of, give yourself another problem that looks like it. So what if I had like 4 times 4 minus 5 times 5 over 4 minus 5? Do you see what I've done? I replaced the
Yeah.
sine thetas. Okay. Could you cancel a 4 and a 5?
No.
Okay. So you're clear on you can't do that if it were numbers, right?
Right.
So do you see that in yours you couldn't do that either?
Yeah.
So that's a good way to always check, like if you're just quite a little unsure on some algebra, just give yourself an example of numbers and see if you would allow yourself to do it that way.
Okay.
Right? Because if you cancel these, what would you be left with? You know, like is that really just 4 minus 5? Like, you know, so if it just doesn't seem right, then that kind of helps you make that decision not to do it.
Okay.
Okay, good. This is all about learning what we can and can't do. Do you have any other ideas then, if that's where you are?
No, not at all.
Okay, let me ask you this. Let me kind of guide you then. How about this? What would the odd identity tell me I could turn that into?
Just sine theta.
Sine theta with a negative in front of it, right? Negative
Yeah.
sine theta. And then I could turn the other one into negative sine theta. And then with the even and odd properties of cosine, I could turn that into cosine of theta times cosine of theta. I could do that, right?
Right.
Right. So on the cosine, there's no negative that comes out. All right. So I don't know if this is going to help us. All right. I'm just showing you this is something from where you've taken us right now. This is something we could do, right?
Right.
Okay, let's keep going. Brianna, what would negative sine theta times negative sine theta be? If we have negative times negative.
Well, it would be a positive.
Positive sine theta, but squared, right?
Right.
And then we have minus, and then this would be cosine squared theta. Yeah?
Yes.
Okay, now on the bottom, we haven't done anything, but we got everything here with thetas. Couldn't we turn this bottom one into negative sine theta? And then minus cosine theta like that?
Yes.
Everyone agree with that? Any questions? Okay. Brianna, do you see anything we can do? Think about when we started this out. Where was it? When we started these problems out, we had like, okay, turn things into sine and cosine. Well, we already have that, right? Multiply
Right.
numerator and denominator by conjugate, single fraction, factoring, right? Do you see any factoring?
Yeah, I was like, I guess you could factor the top.
Top difference of squares, right?
Yeah.
So
What I
that
did
would
was
be
I factored out a -1 before I factored
on the bottom or the top.
on both, and then I canceled out the -1s. And
You
then
could do that. You could factor -1 and then cancel the negative on the bottom. I'm going to stick with this. What I'm about to demonstrate to you right here is that your goal is to get from left-hand side to right-hand side, right? That's your goal, is trying to get from the left to the right. There are multiple paths to go, okay? All right, sometimes there's a very straight, direct way to get there, and sometimes you have to do a bunch of algebra, and some of you are going to do like crazy paths and then finally get there. All right, there is no one exact way to do this. And so I'm going to stick with what Brianna's doing here. And after we're done, I'm going to do it a different way. And I'm going to show you get the same thing. Okay. And that's what's somewhat frustrating about these identities, is that because there's all these different ways you can go, you may take half a page or a full page to show it's true. And then you talk to a friend in the class, they're like, oh no, I just did this, and it takes them like 3 lines. And you're like, oh my God, they're both correct. That's the frustrating part, is not knowing what the clearest path is. And that becomes better with time. All right. So let's do this. I'm going to factor the top. That's a difference of squares. I guess the important thing right now is for you to, if I do something you're not sure what I'm doing, is to make sure that you get that clarified with me. Okay, so here we are. Now, Brianna, I'm going to stick with you here. Can we do anything now? Remember where we're trying to go, right? We're trying to get to this. Maybe I should jot that down. We're trying to get to cosine theta minus sine theta. That's where we're trying to get, right? So can we do anything here?
I want to say you should be able to.
Are you really
I
wanting
really
to
don't know.
cancel? Are you really wanting to cancel something here?
Yeah.
Okay, these both have negatives. This one, they both don't, right?
Right.
These both have positives. But wait a minute, Brianna, these both have negatives. So what could you do if they both are negative? What can you factor out of that?
-1.
-1, okay. So if I factor out a -1, out of the bottom, then it turns them both positive, doesn't it? And now do you see them cancel, Brianna?
Yeah.
Those go away, right? So now we're left with sine theta minus cosine theta over -1. But because you have a -1 on the bottom, you can just, remember with fractions, if you have a negative, like if you have 4 over -5, you can also put the negative on top and it's the same thing, right? So why don't we just make that a positive one and move the -1 on top? So make that a +1, put the -1 on top, and now distribute that -1 through. And we get negative sine theta plus cosine theta, which is the same as cosine theta minus sine theta, which is the right-hand side.
Well, that was fun.
Yeah. So I would say if we were trying to get from left-hand side to right-hand side, I would say the path that we took looked like this. It was definitely not the straight line path,
Yeah.
but it definitely got us there. Okay.
Can you show us the other path, like, and
I'll show you another path. I will show you another one. Okay.
And-
There's no the path. Okay. So no matter what, there's no like perfect answer that's the one, okay? I can show you one that I saw. Okay, here's the one that I saw, and if you saw this, great. Just right off the bat, the top is a difference of squares. Right off the bat. Like this is something squared minus something squared. So if I rewrite that, it becomes sine of negative theta plus cosine of negative theta, and then times sine of negative theta minus cosine of negative theta, with that over sine of negative theta minus cosine of negative theta. Do y'all see that difference of squares on the top? And yes, then okay. And now what?
Cancel
Can I
out
do-
the denominator with the sine of negative theta minus cosine of negative theta.
So turn the bottom into negative sine. Is that what you're saying?
No,
No?
cancel.
Okay.
You can cancel it out from the factor in the numerator.
Oh, from right here, just cancel them right here.
Mhm.
Okay, good. Does everyone see that? They just cancel, boom, boom. Okay, so now we have this. Sine of negative theta plus cosine of negative theta.
And that turns into negative sine of theta plus cosine theta.
Negative
and then
sine theta. So now we use the odd property of sine, and then we use the even property of cosine.
And then just put the cosine ahead of the sine.
Yeah, and that we're pretty much there. Hold on. Doing yard work yesterday, so allergies have been bothering me. Okay, I would say that was pretty clean. Would you? Difference of squares, cancel, and then use the odd property of sine, even property of cosine to get the right-hand side. Okay. It's fun, huh? Let's do the next one. Do you all want me to give you time again, or do you want me to just work it? How about I give you time? I mean, I can sit here all day long and just show you like the direct path, because I've done so many hundreds and thousands of these over my life that it's just, I see the path a lot clearer than you will. So why don't I give you another 5 minutes and just see how far you can get. And I've got another student up here next on the list. I'm not going to say who it is though. 5 minutes. 1 minute. I just launched a poll to see how many of you think I guess you'll know if you got it because you prove it, right? So yes or no? Okay. I think that's enough time. So the results of the poll, 4 students feel like they got it. There is still a possibility that you could think you got it and did something wrong and accidentally get it right. But 4 out of the 16 that were polled, so 25%. So you struggled. A lot of you struggled with this. Okay, that's good. I mean, that's the nature of this. All right. So Michael Clark is the next person on the list. So Michael, are you here? Let's see. Michael Clark. I don't see Michael Clark here. Leslie?
Here.
How'd it go, Leslie?
I felt like I was going in circles.
Yeah, okay. So you started with the left-hand side, right?
Yeah.
Okay, what did you do first?
So the 1 plus tangent u I turned into 1 plus cosine over sine.
Okay, good. 1 plus sine u over cosine u.
Yes.
And then did you do anything with the bottom?
Yeah, so for the bottom I got the same exact thing.
Did you flip it? Was it cosine over sine or sine over cosine?
I had because the cotangent turned into 1 over tangent, but then the tangent turns into cosine over sine. So that's where I was.
Yeah, it's cosine over sine. Is that what you had or no?
Yes.
Okay. All right. Good. All right. I'm with you.
Okay.
Now what? Any ideas?
I turned in the tangent into the sine over cosine too because I didn't know where else to go from there.
Where, on this side?
Yeah.
Okay. So remember, we can't work with the other side.
Okay.
So we have to always start with the one side. In this case, the left-hand side.
Okay.
And our goal is to work all the way down until we can say, oh, look, it's the right-hand side.
Okay.
Right. So you're stuck at this point pretty much?
Yeah.
Okay, good. I'm just trying to figure where everyone was. How about Michael, the other Michael? Are you here?
Me?
Yes, yes. Did you do the same thing? Michael, you're muted.
Okay, can you hear me?
Yeah, I can hear you.
No, this is where I got stuck too.
You got stuck here? Okay. How about Samuel?
I think I did it a different way.
You did? Okay. So did you get it or no? Or did you
I think I got it.
You think you got it? Okay.
Yeah, I
So
think.
we're gonna leave that one. We're gonna leave that one, and we'll see what Samuel did. Okay, what did you do?
Well, I don't know if I was right, but
Okay.
I made a cotangent to 1 over tangent.
Okay. So 1 over tangent u over 1 plus 1 over tangent u. Okay.
And then I added I made the 1 into a fraction and I distributed the tangent.
Where, on the bottom
on the
here?
bottom. Yeah.
Okay, so you rewrote 1 as what, 1 over 1?
1 over tangent u. I don't know if I did that right.
Yeah, you can't rewrite 1 as 1 over tangent. Because that's not 1 anymore. Is that what you did?
You can write it as tangent over tangent.
Yeah.
You could write tangent over tangent. Yeah.
Yeah, that's what I try to do.
Did you do tangent over tangent?
Yeah.
Okay, you can
Like-
do that.
And then I added them.
Okay, so leaving the top alone. You added those together because they now have the same denominator, so it became tangent u plus 1 over tangent u, yes?
Yes.
Okay. This will work if you did the rest right. What did you do now?
Then I multiplied it.
Yeah,
Or-
so
Reciprocal.
reciprocal. So what you have to, everyone, what you'd have to see here is that the numerator is really 1 plus tan u over 1. Okay, that's what the numerator is, right? Anything over 1 is itself. And then you multiply by the reciprocal of the bottom. So if we take the bottom, we flip it, it becomes tan u over tan u plus 1. And there, this 1 plus tan u and this tan u plus 1 are the same thing, and they cancel, and you're left with tan u. Good, that works.
Yeah, I just thought it was easier because it was just working with 1.
Yeah, this path is easy, right? I mean, there's other paths, but this path seemed to go there pretty good. So good job. Does anybody have any questions on that path? No questions? Okay. Did anybody else get it by doing this path? Did anyone go this way and feel like they got it? No? Okay, it works too. So let me show you. I'm going to go back to this one and show you what you could do now. So I'm going to try and save us a little bit of time here. So see if you follow this. What I'm going to do is I'm going to get a common denominator on the top. So I'm going to rewrite this one as cosine u over cosine u. That way these two have the same denominators, right? These two have the same denominators. And then here I'm going to rewrite this as sine u over sine u. And that way I can put those two together. That makes sense? The new numerator will be cosine u plus sine u over the common denominator, which was cosine u. Then the denominator will be sine u plus cosine u over sine u. Any questions on that? We're good. And now, same thing, multiplied by the reciprocal. So I take cosine u sine u over cosine u. And I multiply it times the reciprocal of this, which would give me a sine u on top. And on the bottom, I get sine u plus cosine u. And these two cancel because they're the same thing, right? Cosine u plus sine u is the same as sine u plus cosine u because addition can be flipped around. And because there's multiplication, we can cancel the factors. And when we do that, that leaves us with sine u over cosine u, which just is tangent u, which is the right-hand side. So I would say the left hand this way, what you're doing here is you're turning everything into sine and cosine, which I like this. But then because you have this like complex fractions, you get common denominators, then put together, then divide, then cancellation, then it's just straight out. What do y'all think? Yeah. Y'all want to see another way? I can show you another way. Let's do something different. How about this way? 1 plus tan u over 1 plus cotangent u. Okay, that's the original problem, right? Let me see. I'm trying to think of how this might work. Okay, so here's what I'm going to do, I think. Let me try this. It may not work. I'm going to multiply by the conjugate of the bottom, top and bottom.
That's what I did, sir.
You did conjugate? Did it work?
I got confused halfway through at one part.
Okay, okay, let's see what happens. I think this is going to get messy. Okay, on the bottom, let's do the bottom first. On the bottom, you should get 1 minus cotangent squared u. That's what you should get on the bottom, because you do the ones, the middle terms cancel, and then you get a negative cotangent squared. Is that all right for the bottom, everyone? On the top, I get 1. I get plus tan u. I get minus cotangent u. And then I get minus cotangent u, tangent u. Okay. That's what we get, okay? I mean, it is what it is. You have to see something here. Anna Marie, I don't know, did you say you did this way, right?
Yes, the bottom is equal to secant squared.
Okay, good. So did you see though what cotangent u and tan u become? Did you get that?
They cancel into 1.
They turn into a 1 because
Which
cotangent
cancels out
u,
the 1 plus minus
yeah.
1.
Cotangent u is cosine u over sine u, and tangent is sine u over cosine u. And so cosines and sines all cancel. You're left with a 1. So this is just a 1, right?
And then the ones cancel.
And these ones cancel. This one and that one cancel. So my numerator is tangent u minus cotangent u. Now, the denominator, I heard you say this, Anne Marie, this is very important. This right here turns into something, and you have to go back to the identities and the Pythagorean identities. And you have to look at which one here. We have the one that has cotangent in it is this one. So if I bring that over here, I have 1 minus cotangent u. So, we have a problem. This is 1 plus cotangent u. Do y'all see that? This is 1 plus cotangent u. So the most you could do, yeah, this is going to get really messy. The most you could do is this. You could solve this for cotangent squared u equals cosecant squared, I'll use theta here, theta minus 1. So you can move the 1 to the other side. But that means that this now becomes, oh, it's going to have cosecants in it now. Do you see that? It's going to have a cosecant. I don't like that.
It got complicated really fast.
Yeah, this is getting bad. So hold on. I'm just going to leave it. I'm not going to change it because I believe there's still a way. I'm going to leave it here for a second. What about the numerator? You know, I just don't see a way we can do this without getting it in terms of sine and cosine. I mean, if I were forced to go down this road, I would have to do this minus this. So I'm just rewriting what tangent and cotangent are. Now on the bottom, I'd probably do this. So I'd rewrite cotangent squared u as cosine u over sine u squared, both of them squared because this is squared. And then I'm feeling common denominator coming now. I'm going to continue because I said I would. Okay, so I'm going to get a common denominator on the top. That means I need a sine u here, sine u here, and I need a cosine u here and a cosine u here. Oh my, this is getting bad. Sine, I get sine squared u minus cosine squared u over the common denominator, sine u cosine u, over, I like Samuel's way. Sine squared u minus cosine squared u over sine squared u. So what I did there on the bottom is I turned this into sine squared u, this 1 into sine squared u over sine squared u. So for those of you who are still following along, common denominator on the top, put them together, common denominator on the bottom, put them together. And let's see what happens here. We can now do multiplication of the reciprocal. So sine squared u minus cosine squared u over sine u cosine u, leaving the numerator alone. Now flipping the bottom one, sine squared u over sine squared u minus cosine squared u. Those cancel, which leaves me with sine squared u over sine u cosine u. And because the top is squared, right, because this is really sine u times sine u, one of the signs cancel. I'm left with sine u over cosine u, which is tangent u. Yeah. Not liking that path, but still got there, right? Still got there. Okay. We should do another one. How are y'all feeling about this? Remember when I said, you know, I remember that this as a student as being pretty messy. I mean, the thing is, you know the answer, right? You know that it's you know that it's an identity because they're telling you to establish the identity. So you know that there is some way to get from the left to the right. There's got to be a way. It's just a matter of you figuring out the way. And this stuff becomes very useful later because in higher math classes, we get a lot of trig functions and complicated trig expressions, and we want to be able to simplify them. And this identity stuff is just getting you used to the idea of the types of algebra that you can do with trig functions. All right, it's 10:26. Let's take another 5 minutes here to see how far you can get with this one. All right, check back in 5 minutes. I put the poll up again. So just, you know, when you have time, yes or no. Okay, it's been 5 minutes, and according to the poll, only one person feels like they got it. 13, 14 say, 15 say no, they didn't. So, all right. So the 16 say they didn't. So, I mean, I think the moral of the story here is that this is going to be frustrating. Okay, the homework is going to be frustrating. When I do the solutions for them, it's going to be easy to watch me do it because I'm going to just lead us right down the path. And the only way to get good at this is just to continue to be persistent. And just, you know, if you get stuck, just put that paper to the side, start a new, fresh page, and, just keep going. All right. So this is really going to test your persistence. Are you the type of person who gets a problem, can't get through it, and just wants to quit? Or are you the type of person who can't go to bed until you get it done? I think this is a really good section for establishing whether or not you really want to be an engineer or computer science major or whatever it is. The STEM field requires problem solvers, people who are persistent, right? Can have that motivation to just keep going, willing to fail, and then finally get it right. All right, so the one person got it, I think. So let's go with that one person first. If you're willing, whoever said they got it, if you're willing to tell us. Anna Marie?
Yeah.
Okay, do you feel like sharing how you did it?
Sure.
Okay, so let me write it down first. Oh, I don't want that pen. All right, you started out with the left side, obviously.
Yes, sir.
Okay. And what did you do first?
I got a common denominator between both of them.
Between both of them?
I
Okay, so-
multiplied the left side by sine theta, and then the right side by 1 plus cosine theta.
right. Well, that's right. That will work. I mean, you're allowed to do that. Does everyone understand what's happening here? You need a sine and you need 1 plus cosine theta. So that's what Anna Marie is making happen. Okay,
So
Anna Marie.
then I distributed, so I got sine theta squared on top, and then
Okay.
on bottom I got 1 plus cosine theta times sine theta.
Okay, and then the other fraction, you had 2 terms here, 2 terms here. So you had to FOIL, didn't you?
Yes.
Okay, and when you did
So I got 1 plus cosine theta plus cosine theta plus cosine theta squared. All over
all of that.
1 plus cosine theta times sine theta.
Okay, any questions on this? Started with the left-hand side. Got a common denominator. Now you put them together?
Yes, I put
Okay.
both numerators on top of the one denominator.
Okay, let me do that. Can I put these 2 cosines together right now? Is that all right?
Yes. you
Okay,
got
so when
2
you add those,
cosine theta.
2 cosine theta, and then cosine squared theta, then all of that over the common denominator, which is 1 plus cosine theta, sine theta. Okay, what now?
Then you have the Pythagorean identity with the sine squared theta plus cosine squared theta. So those just equal to 1.
Right? Everyone see that? Sine squared theta plus cosine squared theta really becomes a 1. So now I have a 1 plus 1 plus 2 cosine theta
All over the same denominator.
all over the same denominator. And then I'm assuming you added the 1 plus 1 and got 2.
Yes. And then I factored the 2 out.
Okay, good. So 1 plus 1 is 2, then 2 cosine theta. And then over 1 plus cosine theta, sine theta. Now, why did you factor out a 2?
So I can then cancel the numerator with the denominator.
Yeah, so this you have to kind of see, everyone. If you pull a 2 out of both of these, you're left with a 1 here, and then you're left with a cosine theta in parentheses, and that's exactly what we have in the denominator. They cancel.
Then
That
you're left with 2 times 2 divided by sine. Yeah.
Yeah. So 2 over sine theta is same as 2 times 1 over sine theta.
And then 1 over sine theta is just essentially the same as cosecant theta.
Which is the right-hand side. Good, very good. So again, I hope it's easy to see when someone like does it right. You know, it's the hard part is you finding that path also. Now, did somebody try something else and get stuck? Someone want to share what they tried and got stuck with? Because I might still be able to help you get there. Anyone? Let me call on somebody. How about Caroline? What did you do? You're on mute.
Sorry, I thought I muted myself.
That's okay.
I was pretty much stuck from the beginning. I had a couple ideas as to what to do first, but didn't know which one to pick. Like I thought about getting the same denominator, but I didn't think that was going to work with the plus ones as well.
Yeah.
And I wanted to cross out like the sine thetas, but I didn't know if that was technically like allowed.
Yeah, so you can't because of the plus, right? If this was multiplication, you could cancel them.
Okay, and yeah,
Because
that's
it's a plus, you
what I
can't.
was unsure about.
Yeah. And the way, again, I would do that is, see, you have sine theta here. Let's just make a fraction. 4 over, and then notice this is 1 plus cosine theta, 1 plus cosine theta. Those are the same also. So it would be like, can you cancel those 4s and those 5s? Like, is this really just what?
Well,
Those
then it would just equal 0 and not the 2 cosecant theta too.
What's that?
I said, well, then it would just like equal 0 instead of the 2 cosecant theta.
Yeah, it wouldn't. It would definitely not equal 2 cosecant theta. So something's not right there. All right. What about James? James, did you try something?
Yes, I kind of went the route Caroline went, but I got stuck, and then I had to erase my work. But
Okay.
I like how Anne Marie did it on the left side. I understand that.
Yeah. So, you know, when you see 2 fractions, try a common denominator. It may not look like you're going to get there, but you know, it worked out. We're out of time. So what I would say is start doing your homework and just do as much as you can. There's still, let me see, in terms of examples, there's still a few that I didn't do. What I did is I'm trying to do all the examples that were in the textbook, and they only did 8 examples in the textbook. And let me point out number 8 here. We didn't get a chance to do it, but this problem here, what makes this one interesting, and this is, if you get something like this on your homework, you might just want to wait, is the fact that it's hard to say which side is more complicated, right? Like, is the left-hand side more complicated? Is the right-hand side more complicated? So we'll see next time that sometimes you start with the left-hand side and you start working, and then you just kind of get to a point where you're not quite sure, you know, where to go. And then what you can do is take the right-hand side and start working with that. And then again, you get stuck. But if you can show that these 2 are equal, then you've created a path. Because you just work the left till a point that you're done, you're stuck, work the right till you're stuck at the same point. Then if those 2 are equal, then you have the completed connection between the left and right hand side. Now we haven't done one of those yet, but see what you can do on the homework. I'll do the homework solution videos either today or tomorrow. We'll come back and we'll see where we are. Okay, we'll do some more examples. But for now, let's say the homework is due. Okay, try to do as much as you can. Then I'll extend the deadline. Okay, everyone, have a great day. Talk to you later.
Thank you.
All right.
Thank you.
It's
Bye. Have a good day,
homework
sir.
8.3.